Okay, BC Scout. This is a short lecture for Tuesday. The homework from 7-2. Note, not a digital learning day assignment. That is a separate entity. You should also note the digital learning day assignment needs to be submitted between 2:30 p.m. and 5:30 p.m. on Tuesday, January 10th. I will put together a new editable document that will have the date, January 10th, on it. You need to enter in the patterns that you find in the Vanguard problems, at least 12, remember, for the A+, and then submit that to me after 2:30 p.m., not before. The Google Doc will be time-stamped. You get it to me between 2:30 and 5:30, then I can credit you with attendance on the digital learning day. Okay. Now, on your class page, you'll also note I've scanned the solution manual for 7-1, which was the exploratory problem we talked yesterday, and 7-2, quickies. Make sure you work through those, right? But this video is going to be talking more generally about any function, y is f of x, where the derivative of the function is directly proportional to the function. Or you could say y is directly proportional to the derivative. Either way will get us to the right spot. Okay, I'm going to start from here. The derivative directly proportional to the function. You saw that if y was an exponential function, this will be true. If you tried the converse of that statement, if this is true, does it necessarily imply that y is some exponential function, b to the x? Is that necessarily true? And it will be true. We're going to work through a number of specific examples, and you'll sort of see that this idea of the rate of change being proportional to the function itself always leads to exponential functions, either growth or decay. Okay, how do we go about doing these? Well, there's a method of solution called separation of variables, and that's going to be used quite a lot in this chapter. And what we mean by that is we're going to take this derivative dy dx and consider it as a ratio of two differentials. So I'm going to take the dx, that differential, and put it over here. And then I'm going to take the function y, divide both sides by y. So we have dy divided by y is k dx. Okay, and that's valid as long as y is not 0. But you should remember from your pre-calculus that if you have a exponential growth or an exponential decay, they are asymptotic to the x-axis and they never actually get to 0. So this would be okay. The next thing we're going to do is we're going to integrate both sides. Now, this is sort of interesting on the left. If I consider it as 1 over y dy, that should scream log to you, and that will integrate as a log. And on the right side, k is a constant, so I can pull that out. So I'm simply integrating 1 dx, and that's just a power rule. So let's see. On the left side, I have the natural log of the absolute value of y plus some constant. And on the right side, I simply have kx plus some other constant. Now, almost never will you write C1 and C2. Instead, what we want to consider, suppose we move C1 to the other side. So we have the natural log absolute value of y is kx plus C2 minus C1, and then just call this a constant C. Okay? So typically, when you see the derivative proportional to the original function, the first step, you write dy over y equals k dx, and then you integrate both sides, and you can do it very quickly, and we get the natural log absolute value of y is equal to kx plus the constant, and only put the constant on the right side. Okay. Now, you'll note in this general solution, there are two unknown constants, k and c. And in order to solve this exactly, we're going to have two pieces of information. So let's suppose we were told that y of 0 is equal to 500. This might simulate the money problem we saw the other day. Y of 0 is 500. And then I'll just pick another y value. Y of 1 is equal to 520. Okay? So we have these two pieces of information, and they should be enough to find our constants k and c. And let's see how we could go about doing that. The first thing we want to note is that in both of these situations, y is positive. So this is greater than 0, and this is greater than 0. And since y is bigger than 0, the absolute value of y, which we have in our general solution over there, the absolute value of y is simply the same as y. So we'll make that change immediately. We have the natural log of y, and we have kx plus c. Now, we can put the information in at this stage if we like. So for example, if we take this first data point and say that the y value is 500, when the x value is 0, k times 0 plus c, then that tells us right off the bat that c is the natural log of 500. Okay, and we can go that route. It's actually much easier to play with this equation before we put in the data points, and this is the general approach. If we, instead of using the x and y values immediately, let's go ahead and translate this to exponential form. Now remember the Rosetta Stone translation key. If you have log base 10 of 100 is 2, that's the same as 10 squared is 100, right? So in this case, we have log base e of y is the same as kx plus c. So we can translate that and say e to the kx plus c is equal to y. So hopefully you can do that fairly quickly. Y is equal to e to the kx plus c. Okay, now the next thing that's typically done is to think this process through. After you write it down a couple of times, you can just jump to like 3 steps down. But I have e to the kx times e to the c. Note that when bases are the same, right, you would add the exponents. 10 squared times 10 cubed is 10 to the 5th. Right, bases are the same, so you add the exponents. Well, that's what I'm doing here. At this line, I have it added, so I'm just going to rewrite that as e to the kx times e to the c, so I can just add the exponents up and get that. Now, note that e to the c is another constant. Well, c is one constant. E to the c is another constant. So now we have y is a constant out front here, e to the kx, like that. Okay, and technically these are different constants. If we have little c, let's go back to the beginning here. At this stage, let's suppose I call this constant over here a little c, little c, little c, little c, and then e to the little c I'll call a new constant, capital C. A lot of times I'll put these little arrows on there to indicate that's a slightly different constant. Okay, if you want to use b or k for the constant, that's okay too, but we already have a k there. Probably not a good idea to use another k. Now, let's go ahead and look at our two data points. Y of 0 was 500. If we plug that in now, we get 500 is the y value. C e to the k times 0. Well, e to the k times 0 is the same as e to the 0. Right? E to the 0, k times 0 is 0. And e to the 0 is 1. So we have 500 is equal to c times 1. So this capital C is 500. Okay, we're going to put that back into our general solution again, all the way back here. So now let's see what we have. We've got y is equal to 500 e to the kx, right? We've calculated that capital C to be 500. Well, we still have an unknown constant, but luckily we have another data point. Remember, the second data point we had was y of 1 was 520, and I had just sort of made that, let's suppose that's the case. Here, y is 520. That piece of data will now allow us to figure out the constant k. Let's see how that works. Okay, let me pull up a new page here. So we have y is equal to 500 e to the kx, and we know that y of 1 is 520. Okay, so we'll put that information in. The y value is 520, and the x value is 1. Okay, and our task is to solve for k. Well, that's not terribly bad. We'll divide through by 500. So we have 520 divided by 500 is e to k, right? K times 1 is k. We're going to try to solve for k. So once again, use your Rosetta Stone. 10 squared is 100. It's the same as log base 10 of 100 is 2. Okay, now we have this exponential form. We have e to the k is 520 over 500. And yeah, I could reduce that if I want. But I'm going to rewrite that and say now k is equal to the natural log of 520 over 500, right? Okay, so k is the natural log of 520 over 500. And now we can put that back, once we figured out what k is, we'll put it back in our general solution. And we're trying to narrow down the problems here to come up with what y is. Okay, so we have y is equal to 500 e to the kx, but k was the natural log of 520 over 500 times x. Okay? And once again, we're going to note that there's some things we can do with this. Let me take, and instead of multiplying the natural log of 520 divided by 500 times x, I'm going to write it this way. 500 e to the natural log of 520 over 500, and I'm going to raise that to the x power. And you go, geez, what happened? Well, nothing beyond algebra 2. Remember, if we had 10 squared cubed, if we had that, you could rewrite that as 10 squared times 3. That's 10 to the 2 times 3 power. So that's what we're doing here. we have this exponent natural log 500 times x. And I'm simply rewriting that as the quantity e to the natural log of 520 over 500 raised to the x power. Now, why do I do that? Well, from pre-calculus again, you should note that e to the natural log of stuff is stuff. So this parenthetical expression here can simply be rewritten as 520 over 500. So we have y is equal to 500 times 520 over 500 raised to the x power. Okay, and that in fact is our solution to the problem. That is the function that has a derivative that's directly proportional to the original function. A couple of cautions here. You cannot cancel, so don't try canceling the 500s. That would be wrong. Remember, exponentiation always happens before multiplication. So you have to carry out the exponentiation first. Now let's just double check. Does y of 0 equal 500? Question mark. Well, if we put 0 in for x, we get y is equal to 500 times 520 over 500 to the 0 power. Anything to the 0 power is 1. So this is 500 times 1, which is 500. Okay, so that does check, right? Yeah. And the second thing that we wanted to check was making sure that if when we put 1 in for x, we got 520. So does y of 1 equal 520? Well, again, reasonable, easy check to do. We're going to put 1 in for x, so y becomes 500. I'm looking at the specific solution here, times 520 over 500 raised to the first power. And now you do the exponentiation. 520 over 500 to the first is 520 over 500. Then you can cancel the 500s, and we get 520. So that's valid as well. And the last thing we should probably check is to make sure that when we started, we said that the derivative, dy dx, was supposed to be proportional to the original function. And if we just go back to the function here and just look at the derivative, we did this generally yesterday, but dy dx, right, the derivative of this function, 500 is a constant multiple, so we leave that there. This is the exponential part, and we know how to take the derivative of exponentials. You leave the 520 over 500 alone. It's still to the x, but now we have the natural log of the base, which is 520 over 500. And sure enough, this part right here is the original function y. That's y. And so we have dy dx is y times this constant. And again, we had denoted earlier that the constant was the natural log of 520 over 500. Okay. Now, learn how to do that. I'll go through a similar problem. In fact, let me just give you one. Let's do one where we have decay. dy dx is equal to ky, and y of 0 is 100. We have 100 grams of some uranium. Y of 1, and that's going to be at, I don't know, 85. So we have a decay type process going on. Here's the picture. This is x, this is y. We start here at 100, and at x is equal to 1, we've dropped to 85. Okay, so this will be an exponential function again, but now this is a decay process. And so we're going to go through, the whole process again. I'll try to speed it up this time a little bit. I don't want to scare you. These go very quickly after a while. In fact, there are some shortcuts you can use sometimes. But let's go ahead and solve this particular differential equation with these two conditions, that the initial amount is 100, and after a time period of 1, we're down to 85. Okay, dy divided by y is k dx. Integrate both sides. natural log of y. I'm not even going to put the absolute value because, again, I'm looking, these y values are positive. So the absolute value of y is y plus c. We exponentiate. We have y is e to the kx plus c. And immediately we're going to write that as a different constant, capital C, where the capital C is e to the c, right? Capital C, e to the kx. Okay, we're going to put in our first initial condition. We know that y of 1 is supposed to be, or sorry, y of 0 is supposed to be 100. Y of 0 is supposed to be 100. So if we put that in, we get 100 is c e to the 0, right? C e to the 0, x being 0. And so c is 100. C is 100. So we can put that into our general solution here. Y is 100, e to the kx, and then we'll put our second condition in that y of 1 was 85, we said, I believe. Yeah. So y of 1 is 85. We'll put that in. 85 is the y value, and the x value is 1. Okay? Maybe we should, just to change it up a little bit, let's call this 2 instead of 1 so that we have a different x value. So this is going to be 2. So this is 2. So it doesn't always have to be 1. And in fact, the initial condition doesn't have to be 0 either. But now we have when x is 2, y is 85. So again, we're going to solve for k here. So we have 85 over 100 is e to the 2k instead of k2. That sounds like a large mountain in the Himalayas, but k2 we can write as 2k. So we exponentiate both sides, and we have the natural log of 85 hundredths is k. So k works out to be 1/2 the natural log of 85 over 100. Okay, now we're going to take that and plug it back into our general solution up here. So now we have y is equal to 100 e. K works out to be 1/2 the natural log of 85 over 100, and that's times x, right? So there's the x up there. We figured out what k was. K was this quantity. Okay, but then once again, I want to try to clean this up. I see e's as a base and natural log as part of an exponent. So the 100, I'm going to have e to the natural log of 85 over 100, right? That's going to simplify, and then I have to the x over 2 power. Okay. So y is equal to 100, 85 over 100, and the exponent is now x over 2. Okay, and that would be the solution to this decay problem. Let me give you one more piece. Well, we'll talk about this on Wednesday, assuming we're here Wednesday. If not, we'll talk about it Thursday, or I'll do another video. When you have any growth or decay situation, the derivative is directly proportional to the function, and you're given 2 data points. So let's say this is 0, 3, and there's another point out here which happens to be 5 and 7. Okay, you can immediately write down the solution. Now, you should be able to do the separate and integrate because there's lots of functions that have a differential equation that are not strictly proportional to the original amount. Okay, but if that is the case, then there's only one solution that fits here. Y is going to be 3. 3, that's this quantity. And then you're going to have 7 over 3. The 7 comes from here. And then you're going to have the x over the 5. And the 5 comes from here. Note that this is exponential. Okay, it certainly is an exponential function. The base happens to be 7/3. the exponent is variable. Okay, and just to double check and make sure that it goes through these 2 points, if x is 0, let's see what we get. We get y is equal to 3 times 7 thirds to the 0 over 5. Right, 0 over 5 is 0. 7 thirds to the 0 is 1. So this works out to be 3, which is what we needed. That was the first point. Suppose x was equal to 5. Let's see what happens. If x is equal to 5, then we get y is equal to 3 times 7 thirds. X is equal to 5. And so 5 over 5. 5 over 5 is 1. 7 thirds to the first power is 7 thirds. And the 3's cancel, and we get 7, which is this one. Okay, so we do have the correct function here. No problem. That's our exponential function that meets these 2 criteria. And it will work for growth. It will also work for decay. Okay, so go ahead and start to work through the exercises out of 7.2. I have copied the pages from the solution manual, so you should be comfortable with 7.1 now, all the quickies out of 7.2, and you're working through the exercises on 7.2. If you look at the general assignment for the second semester, I think we budgeted a couple of days for these problems. Okay, let me stop this here. 20